Hi everyone, I hope you're doing good. My name is Igor, and today I'll be talking about Apple's AppAttest API. So I'll tell you how this technology works and what is our options if we want to bypass this check. So let's get started. Currently, I'm working as mobile security expert at Thales DIS. My average working schedule includes reverse engineering, penetration testing, code reviews, and sometimes I conduct security trainings to our developer teams. So annually, I interact with more than 10 different developer teams and support around 30 projects that need significant level of mobile application security. Our today agenda is to discuss what's the AppAttest API technology is. So this technology was released by Apple, and in order to help developers to increase the security level of their applications. We'll see what this technology is, what's the right motivation to implement and start using it, and most important part, we will see how actually good it is and what is the current bypass possibilities for potential attacker. This talk is mostly for mobile application developers and defensive teams who consider on implementation of additional protections to their anti-tampering mechanisms. I think it's necessary to describe a potential use case for this technology, so you can get to the point yourself when you can say, like, God damn, I need to have this technology in my app. So, because using something related to security without exact understanding of how it works can give you a false sense of security, which is kind of not good at all. So regarding the topic coverage, I want to declare that this talk is focused on client-side security of mobile applications. So it's mostly about the things that happening on the user's mobile device. But however, we will see how client-side security part could be improved with the server interaction, because AppAttest API is not a standalone solution and requires you to be connected to the internet. Now let me name those client-side protections that mobile application developers want to implement sometimes. So maybe based on the requirements or recommendations of different standards, we know there is a wide range of protections, starting from most popular things such as basic SSL pinning or root or jailbreak detection. And it goes to more advanced things, including source code obfuscation, hooking and tampering detection, and other detections aiming to make hackers' life harder. And since we are talking about anti-tampering defense mechanism, it's good to elaborate what tampering is. So tampering is the process of changing a mobile application. For example, during the penetration test, an application might refuse to run on your jailbroken test device, making it impossible to complete some of your tests. And in such case, you will want to change the application's behavior and just turn off this root detection check or jailbreak detection check. And maybe another example that you should be aware, because it's more harmful. For example, crackers or modders can modify your application to enable premium features without paying for that. And obviously, anti-tampering functionality protects the application against such kind of modifications. It monitors the integrity of the application state and environment in which it is running. I'll definitely recommend you to visit Avasp MSTG website. It has a lot of information and detailed descriptions on tampering and anti-tampering techniques. So you can find it there. Now I want to quickly name currently known and popular protection methods against anti-tampering, which are always implemented on the client side. First one is the signature check, the most trivial one. It checks the signer's certificate, and this approach could help you to detect the modification applied to the original app once it's been resigned. Second one is a code integrity verification. It checks whether some specific part of the code has been tampered with by computing its signature at runtime and check it with pre-computed hard-coded hash of its content. And the last one is a resource integrity check. It verifies the signature of specific resources at runtime. For example, these resources could be an image or other assets inside the application bundle. And unfortunately, in the end, attackers always wins and bypass these kind of checks. This is particularly true in the client-side security if we are talking about. So, well-equipped attacker has a natural advantage always. And once the protection mechanism is well studied, nothing stops you from switching all protections off. And the good news is that dealing with multiple protections sometimes is highly complex and could take a lot of time and definitely money to spend. And the state-of-the-art client-side protections are really hard to bypass sometimes. You can't just switch it off using known methods or standard tweaks and tricks. To defeat them, you really need to go through a really meticulous manual analysis, I would say. All right, if we can trust the information coming from our device, and client-side protections eventually could be just switched off, so maybe we can rely on our backend in this case, or even Apple's backend servers. So yeah, I think you get the point. And we're going to talk about Apple AppAttest API. So, and when Apple announced it, my first impression was like, yeah, that sounds interesting. And our developer teams would definitely be grateful if they don't need to code the whole verification logic on the back end from scratch on their own. So let's see what it does. And finally, yeah, it was a quite long intro. We can start discussing the technology itself. So AppAttest API was announced and released 1 year ago. And official announcement says that this new AppAttest API helps protecting against security threats to your apps on iOS 14 or later, reducing fraudulent use of your services. And with AppAttest, you can generate a special cryptographic key on a device and use it to validate the integrity of your app before your server provides access to sensitive data. All right, reducing fraudulent, it says. This description is quite short, and if you don't understand what it exactly means, I can say you're not alone here. So yeah, initially it was quite uncertain to me as well. I checked the documentation, all related articles and presentations from WWDC 21, and it still wasn't clear. So yeah, I was like, what exactly this technology is doing? And is it anti-tampering, or how can I implement it properly? Do I need to code my own detections to support this technology, or I can use it as is and just stop worrying about all these hackers around after I implement it? So, okay. Then I thought the best way to deal with all these assumptions is just to implement this technology on our own and test how it works and whether it's possible to bypass the detection check. And as I said, AppAttest is kind of relatively new technology. And first of all, we need to make an intro to this problem. On the screenshot, you can see the default image of interactions between application on client side and backend on the right side. You can use the AppAttest class to generate a special cryptographic key on the device and have Apple to verify the validity of that key on their backend. So then you can use that key to assert the validity of your app whenever you request sensitive data from your server or want to record some value on your backend. Now let's talk how it exactly works, because it's kind of unclear from start. During my research, I've made a sample app to understand how the whole concept is working and did a little portion of reverse engineering to see what is happening on the device when we're interacting with the API and what could be altered on our side. This application is written in Flutter. I tested it on iPhone 8 under iOS 14.0.1. And yeah, forgive me for that, but I hard-coded some values that depended on backend interaction because I didn't coded a whole implementation of backend server during this research. But yeah, on the screenshot, you can see that functionality is quite simple, but that's enough for our evaluation. And later on, in the end of this talk, I'll share the link to my GitHub page where you can get the sample app and source code to test your own bypasses and maybe other test cases. All right. It's necessary to say that in the whole process, 3 parties are involved. First is a mobile device running under iOS 14 or higher, then backend server under our control, and third party is Apple's backend server. And yeah, now let's see which steps we need to do to complete the attestation process and start signing our outgoing requests. So on the first step, we are generating initial key value, which is unique to the application and contains device identifier. After we call generate key function, it creates cryptographic key. using secure enclave processor. And secure enclave is a hardware-based key manager, which is isolated from the main processor. And from my point of view, hardware-based cryptography, like without leaving a device, it sounds safe enough, sounds good. Then, after we generated this key, we request generation of the challenge on our backend server, just to stay protected from replay attacks and as additional trusted source of data when interacting with our backend. Yeah. So during this step, we are generating a hash value, and we will be using it as a parameter to the attest key function call on the next step. So in the right corner, you can see the example of this hash value. In our testing app, this value is hard-coded, which makes it vulnerable to replay attacks. But fortunately, this type of attacks is beyond the scope of our research. As I said, on step 3, we need to call this attest key function in order to receive attestation object from the Apple's backend server. So this function, as you can see on the screenshot, it takes 2 input values, the key ID value that we got on step 1, and this anti-replay hash from our backend. So Apple recommends to use the SHA-256 hash value, its implementation from CryptoKit. So you're willing to decide how you want to implement it. And yeah, then step number 3, after we call this attest key function with all necessary parameters on our iPhone actually sends outgoing requests to Apple's server. And in the response to this request, we receive attestation object. It's a really, really huge piece of data. Even won't fit in the reference corner. So yeah, it's cropped here. And what is this attestation object actually? So attestation object contains information about device hardware of the requester, application bundle ID, and other sensitive values. And it's very important to parse this attestation object properly on our backend server, because one of bypasses that I encountered was related to incorrect processing of this data. Then during step number 4, we send values generated during all 3 steps to our backend server, where attestation object is the resulting value from step 3. Key ID is a value generated during step 1, and challenge is a client data hash value from our backend server generated during step 2. Then during step 5, we need to verify the attestation object on our backend. So we need to decode it as a CBOR compatible format and store this data on our server and link it to the corresponding user. So you need to validate the team identifier and bundle identifier, so they must comply with the signature expected for your application. Now let's talk a bit more about these validation steps, what this CBOR thing is, and which values we need to take care of and interpret properly. After you stored the attestation object on your backend, you need to decode the attestation object using CBOR parsing library, as I said. Sorry for this, for me repeating myself. You can actually check the example of this decoded object in the end of step 3. And yeah, first step, you need to verify X5C value, that it contains AppAttest root certificate, which is publicly available to be downloaded. You can find the link in the documentation. Then you parse this AppAttest root certificate, obtain the value of CredCert extension. After that, you create hash of the public key in this stored in this CredCert and verify that it matches with the key ID identifier from your application generated during the step 1. After that, you compute the new SHA-256 hash of your application's ID and verify that it's the same as the authenticator data's RPID hash. I don't know why, but still it's necessary to verify that authenticator data's counter field equals 0. I have no idea why they recommend to do it. Then you need to verify the AAGUID field. So it's either AppAttest develop if operating in the development environment, or AppAttest followed by 70 bytes if operating in the production environment. Actually, it could help you to detect whether possibly tampered attestation object was incorrectly assembled using maybe development certificate or something. So it could help in behavioral analysis. So then you verify that the authenticator data's credential ID field is the same as the key identifier from step 1. And after successfully completing all these steps, you can trust the attestation object. Actually, yes, I agree that recommendations from Apple is kind of good and efficient, but the problem mostly can occur on integrator's side if validation is not properly implemented. Then step number 6, it's kind of optional because but you still can use the receipt that was extracted from attestation object during previous step and send it to the Apple server to get the metric, as their documentation says. What is the metric, you would ask? So actually, response body from the Apple server has risk metric field, so which is integer value that indicates the number of attested keys associated with the given device over the lifetime of the device. So kind of small piece of knowledge, in my opinion, but still maybe it become more useful in the sometime in the future if they add more fields to this metric. Next one. Server-to-server interaction. Here you can see that it's declared that this metric can grow if user reinstalls the application, restores from a backup, or transfer a device to another user. So yeah, for privacy reason, AppAttest keys stored on device, they don't survive these events, and you have to generate a new key on the same device. And this metric from Apple could help you in identification of potential API abusers. However, in the end, it's just a number, and only you decide whether you want to interpret this information as something suspicious or not. And it's necessary to remember that Apple doesn't provide a solution. It gives only additional source of information. Step number 7. As you might note, we cannot generate attestation object each time when we want to verify the request, because it would mess up the whole metric on Apple backend. So we will use another object related to attestation object. It's called assertion object. If you successfully verify the attestation object on your server during the step number 5, you can associate the key ID, which you got from the step number 1, with the user's device for the future reference. You need the key ID identifier to generate assertions. Or in other words, you need this key ID identifier to be able to sign requests going to your backend servers. Actually, assertion object and attestation object are both coming as CBOR objects. So far, I saw almost every popular programming language has its own library to parse and decode CBOR. And yeah, even the sort of fresh technology, Flutter and programming language Dart has its own CBOR decoding library. And if you're interested in analyzing its content, I've implemented inbound CBOR decoder inside my sample application, and you can play with it if you want. And if I remember correctly, step number 8 is the last step. Finally, we need to verify this assertion object on the backend. So after receiving the client ID data, which is request body and the assertion, you need to verify and decode the assertion to ensure it uses the CBOR data format and has the expected contents. After assertion is verified, you can trust the request and consider it as not tampered. Let's quickly go through the process of assertion object validation. And I can say it's mostly the same with the attestation object verification. You can check that incoming server request was signed with previously generated private key and all necessary hashes are the same. And after assertion is verified, you can trust the incoming request and consider it as not tampered. All right, finally, we finished with the implementation process of this technology. But does it mean we are protected now? I mean, if we passed all these 8 steps, here you can see some assumptions and remarks made by Apple on their forums and even in documentation. And to me, it sounds really confusing because it's almost impossible to say, for example, that you have 100% evidence that you know what is going on at user's device, that it's not jailbroken or it's not tampered. How could you say that it's not tampered from the very beginning? Yeah, on this screenshot we can see a kind of not clear acceptance of the fact that they can't do much against jailbreaks in terms of detections. And yeah, somehow you need to figure it out on your own, probably. And one more funny slide is brilliant official answer about possible hooking or patching of the attestation call. And yeah, frameworks engineer says literally nothing you can do with it. So don't be surprised that you have to implement much more detections apart from this AppAttestation thing. Now let's talk about all these bypass-related scenarios. All current bypasses are quite simple and depend on the fact that AppAttest can't detect whether device is jailbroken or application was tampered before initial installation on the fresh device. Neither detect hooking frameworks, which are modifying behavior of your application during runtime, during its runtime. We don't even need to hack the key generation algorithms, break the cryptography, because it's really tough. It depends on secure enclave, and in our case, definitely not that efficient to attack through this channel. So we don't need to do that because we can abuse the developer's logic. Fortunately, you saw there is 8 steps and there is plenty of space to make a mistake during the implementation. From my experience, I can say that I haven't seen a single application which properly implemented AppAttest yet. In all instances, it was possible to bypass the check. I mean, literally, you can bypass it by abusing its logic. And here is the cases. Number 1 is quite simple. Do you remember we need to start the attestation process during step 3, which requires internet connection. It's kind of crucial step. So we can just drop outgoing requests by configuring the meeting proxy or using Frida hooking framework. And in some cases, application logic handling this case as a scenario when Apple server is down or not accessible, and continue working with when internet access disabled, for example. In this case, bypass works actually. And yeah, sometimes it requires more throughout checks that validates that you can interact with your own backend server, but somehow you cannot interact with Apple's backend server. Yeah, which means something is going wrong, but none of examples that I saw had such type of check on their side. Next scenario is, so yeah, my favorite one, which works every time as of today. You need to return that iOS version is less than iOS 14. You know, many developers, they are not ready to drop all users who are using devices below iOS 14 yet, and it may take few more years to make AppAttest API usage mandatory on their side. So you can just hook the value, the return value of platform API when it checks the iOS version, and you are able to bypass this check. It just won't trigger the whole key generation logic. Yeah, here is a small piece of statistic regarding that. So it says that 10% of all iOS and iPadOS devices, which is around 100 million of unsupported devices, are below iOS 14. And I think this version related bypass will be most efficient thing for some time until iOS versions less than 14 is end of life and not supported anymore. I've heard an opinion from one application developer that Apple has an ability to validate the signer's provisioning certificate on their backend before returning the attestation object. It was his understanding of the AppAttest API description. So in simple words, his assumption was that Apple can see that I resigned the app with the developer's provisioning certificate, with my own certificate. And Apple could detect it somehow and just don't allow me to start this key generation process. And as you can see on the screenshot, it was kind of wrong assumption, and anyone can modify your app, patch its logic, and resign it, and still generate valid attestation object after all. And yeah, it will be assembled with wrong values to your backend, but at least it still remain valid in terms of its format and Apple's signature in it. So if you parse it right, it won't be valid on your backend. However, as I described before, once I saw the case when attestation object was not correctly processed and literally any value was correct for to the backend until it's properly packed CBOR object. So please remember to implement and test everything as it's recommended in the documentation by Apple. Okay, now I think it's time to summarize all the benefits and bottlenecks that AppAttest API gives to us. So on the bright side, we can use it definitely against the replay attacks if we trust the whole process of key generation and stuff, definitely. Some companies can really benefit from implementing this fraud metric analysis, and maybe Apple can extend the list of metric data in the future. It really could increase anti-tampering protection as additional layer of security by leveraging bypass complexity for already implemented RASP checks. So in other words, I want to say that if you need anti-tampering, you still have to code a lot of things on a client side. And maybe in the future, it really might become an industry standard once it's supported by 100% of iOS devices. Why not? I think it will be harder to find logical bypasses for this technology. And now it's time to summarize all the bottlenecks. On the constraint side, it's still not possible to validate if application is already running on compromised device. So if device has been jailbroken after the key attestation, all the new assertions might be tampered. So, and you won't detect even using this Apple's fraud metric, because you can just hook the application behavior during the runtime, and the outgoing request will be signed on using the valid attestation. So you will trust the object on your backend. So there is no reason to try to break the signature method if you can just tamper on values before signing the request. Then it's, kind of useless as of now, because it has multiple design issues, and success of this implementation strongly depends on the integrator. So there is a human factor in it. One more limitation is that if you're developing app extension and want to use the AppAttest API, you can't, because it's not supported. And I don't know whether it's a big concern, but you still depend on the third party. You depend on Apple's backend server, and if it's not working, so I understand it's unlikely it won't be working, but if it happens, it means your app is not working as well. And as I said, the number of unsupported devices is still very big, so developers are not ready to drop all these potential users to their app to improve the security. And now it's time to decide to answer the question if it's worth to implement this technology or not. Actually, the simple answer is that you need to listen to your security experts, security champions. You need to understand your risk level and threat model. And if you really decide to implement it, and if you are confident to have it properly implemented, you have to be ready to work with all possible caveats on your own. So as we just discussed, it won't help you. So the AppAttest won't help you to identify if device is jailbroken or not. So, which means you have to implement jailbreak detection, and it have to be on client side, which, as you remember, could be easily tampered sometimes. But okay, then to fight with runtime instrumentation and dynamic analysis, you need to implement your own hooking detection and debugger detection checks. And still, even despite AppAttest is sort of anti-tampering solution, you need to have client-side anti-tampering protections to make it harder to statically patch your app and resign it. Because you remember the bypass scenario number 2 or number 3. Yeah, it was number 3. We just patched it and resigned the app. So AppAttest won't even trigger it in this case. And in the end, definitely quite important part to make attackers' life harder. You have to implement obfuscation layers. It must be strong enough to increase the whole analysis, the complexity of this process. So in conclusion, I want to say that we can't create trusted anti-tampering check using only this API. So evaluated solution should be backed up by current client-side protection mechanisms, which are well known and described on the different resources such as Avast MSTG. So I'm talking about anti-tampering, jailbreak, hooking detection. It will help you to ensure that information provided by AppAttest is not modified in the first instance. Sometimes even prior the first usage of this AppAttest API. We also have to take in consideration that this API is available only from iOS 14, and yeah, we have to wait until it supports vast majority of Apple devices, and because of that, I recommend to implement this technology only in experimental mode, and definitely following the close interaction with your security team, because it's necessary not for every product. It costs money to achieve the sufficient level of protection. So make sure it's really necessary for your project before starting playing this cat and mouse game with the hackers. And trust me, they are always competitive, always find bypasses, and you need to improve your protections continuously. And yeah, definitely, I believe there is always a room for improvement. So if you feel that something could be improved in this analysis or in the whole talk, the explanation part, so don't hesitate to reach out to me. I'm planning to continue keeping an eye on this technology to see how it evolves, or whether other bypass scenarios are possible. Here you can find the link to my GitHub repo with all code I used for this presentation. As I said, my implementation doesn't have a full-fledged server side. So if you really need it and don't want to code it from scratch, please take a look at this nice second repository with the server-side implementation. It's written in Kotlin. And yeah, you may want to check OWASP MSTG if you want to know more about attack techniques and protections that we discussed today. And the last batch is related to official documentation from Apple. Kind of must read if you want to get more details about this technology, but be ready that documentation sometimes is confusing. And that's mostly it. I want to say thank you for watching this talk. And yeah, huge respect to the organizers of this conference. So for many of us folks interested in cybersecurity all over the world, yeah, we are happy to have such events during this COVID pandemic time. Yeah, hope to see you IRL in the maybe next year. So yeah, goodbye everybody and stay safe.